All right, we are on to chapter 13, Sheaves of Modules. So when we first talked about sheaves, the only examples of sheaves we had were sheaves of functions on our varieties. Now, when we started talking about schemes, we had more examples. The structure sheaf on a scheme can have values in different fields at different points, so that was something kind of new. It turns out even for varieties, we need to have this sort of thing where the sections have values in different fields or different spaces at different points of your variety. So the sort of motivating example for this chapter is the tangent sheaf. So let me just write down the definition, or sort of an intuitive definition of the tangent sheaf, and hopefully soon we'll make this more precise. So the tangent sheaf, Tx, so x is let's say a variety for now, and we have to tell you what its sections are on some open subset U of x. Well, its sections are going to be elements phi, where phi is given by phi p for each p a point of u, and each phi p is going to be an element of the tangent space to p at x. All right, so we defined what the tangent space is. Hopefully you also have a sort of intuitive notion of that. Okay, and then we should also require that phi p is somehow varying nicely with p. You don't want to just have completely arbitrary elements here. They should sort of vary continuously in some way. All right, so we'll try and make this precise later. But for now, here's a picture. This is supposed to be a visualization of a section of the tangent bundle on the whole space. So here's our variety, P1 of C. So it's topologically it's just a sphere. At each point of the sphere, there's a tangent space. So here's a picture. This little square here is supposed to represent the two-dimensional tangent space. And then at each point, we pick a tangent vector. So that's what this little arrow is supposed to represent, a vector in this tangent space. So that arrow is phi p. And then for each point of the sphere, we have phi p. Now, of course, this picture doesn't show every single point. It just shows, some of the points that land right on this grid. But you're supposed to imagine there's a little arrow attached to every single point of the sphere, and they also sort of vary continuously. Okay, and notice, there's not like one global, even though all these tangent spaces are two-dimensional vector spaces, there's not one single global tangent space that they all lie in together. If that makes sense, the tangent spaces are different at each point. So there, for example, there's no such thing as a constant vector field on the sphere. Right, okay. So a section of the tangent sheaf is sometimes called a vector field. Okay, there's no constant vector field on the sphere because all the tangent spaces are different. Now, also up to now, all our examples of sheaves have been sheaves of rings. The tangent sheaf is not a sheaf of rings because you can't multiply tangent vectors, right? The tangent spaces have the structure of like a vector space, not a ring. So yeah, so let me write that down. You can multiply by scalars. Okay, or sort of more generally, if you're looking at a section over U, so you can multiply, let's say f in OX of U, so this is a regular function on U, by phi in the tangent space to x of U. All right, this makes sense because you could just think of f as being a scalar at each point of view, and phi is just a tangent vector at each point of view, so you can multiply that scalar by that tangent vector, and that makes sense. All right, so this is going to lead us to our definition of sheaf of modules in just a moment here. All right, so what's the definition of a general definition of a sheaf of modules? So a sheaf of modules is a sheaf. So recall our definition of sheaf. Go back and review that if you need to. And it should be on a ring space. Space X OX such. So let's name our sheaf F. So such that for all open subsets U, F of U is not a ring, but an OX module, an OX of U module. Okay, and furthermore, we require that the module structure is compatible with restrictions. All right, so what do I mean by that exactly? I mean, if I have two sections, phi plus psi, and you restrict them to a smaller subset of v. So let me say phi and psi are in f of u. Okay, now because f of u is an OX module, modules in particular have additive structure, so you can add two things. So phi plus psi, we can add them, and then we can restrict to a smaller open subset v, but that should be the same as if you restricted to v first and then added. Okay, and the same thing for the multiplicative structure. So now let's let lambda be an element of OX of u from the structure sheaf, and I want to say that lambda phi restricted to v is the same as lambda restricted to v times phi restricted to v, where here lambda dot phi is supposed to be the module action, right? All right, so these two conditions give the compatibility of the module structure with the restrictions. All right, so this will be called a sheaf of modules, or sometimes maybe I should call it a sheaf of OX modules, if I want to specify the structure sheaf here. All right, and maybe I should also say that, of course, there's also pre-sheaves of modules, but sheaf is easier to write, and we'll mostly be using sheaves more than pre-sheaves. So let me just write down sheaf. All right, we should also define morphisms of sheaves of modules. So let's let F and G be OX modules, okay, on the same space with the same structure sheaf. Then a morphism of OX modules is for each U open subset of X, and OX of U module map. So remember, OX of U is a ring, and F of U is an OX module. So all right, so F of U is an OX of U module. G of U is an OX of U module. So we have an OX of U module map. So let me call it morphism F. So, and I'll just denote that map also by F. And it should be compatible with restrictions. So let me write it down here so I have room to draw the diagram. All right, so maybe you can guess how this diagram is going to work. So if I have a smaller open subset V, then there's a restriction map from F of U to F of V because F is a sheaf. There's also a restriction map here, and there's also f ox of v module map here, and this diagram should commute. Okay, so that's a morphism of ox modules. So according to the definition, you have to specify these maps for every single open subset. But we'll see in examples that usually there's concise ways to describe these morphisms. All right, let's do some examples. We'll start out with sort of the trivial examples, and then we'll get to a more interesting one. So OX itself is an OX module. All right, so this is sort of analogous to, a ring is a rank 1 module over itself, right? So, OX of U is a ring, and it's a OX of U module for every U. All right, so that's sort of the most trivial one. If you start out with 2 modules, so if you have F and G OX modules, then you can form their direct sum, right? F plus G is an OX module. And how does that work? Well, you just take F plus G on an open set U is just the OX module G of U direct sum. Or sorry, let's do it in the right order. F of U plus G of U. All right, so if you know how to take direct sums of modules, there you go. Okay, so in particular, this could give us, the rank R trivial module. So OX plus R, we'll call this the rank R trivial sheaf or trivial module. Okay. All right, so here's our first interesting example, and a very important example that comes up quite a bit. These are called the Serre twisting sheaves on PN. I think our textbook just calls them twisting sheaves, but I think it's common to call them Serre twisting sheaves. Okay, and so what we need to do is we need to pick a D in integers, and for each D, we'll have one of these sheaves on Pn, and it's going to be called OPN parentheses D. So remember, the structure sheaf was called OPN, but if you put parentheses D after it, then we're talking about one of these Serre twisting sheaves, which is a sheaf of modules on Pn. All right, so to define the sheaf, we need to tell you what the sections are on an open subset U. So here's the sections. It will be things of the form G over F, where F and G are homogeneous polynomials in the homogeneous coordinate ring of Pn. So homogeneous with degree of G minus degree of F should be equal to D. So this quotient here is supposed to have degree D, and it's the degree of the quotient is defined by the degree of the numerator minus the degree of the denominator. Okay, and furthermore, we want this to be sort of well defined on U. So we want F of P not equal 0 on U. Okay, of course these don't form a well-defined functions because they're not on projective space because they're not degree 0. But at least we want the denominator not to be not 0. And when we're considering this as a subset of the fraction field of the polynomial ring, meaning that if you can like cancel out some terms or something, then those count as the same section. All right. And then just to be careful here, let's say this definition appears for non-empty subsets. For the empty subset, we'll just define it to be the zero module, right? So the zero module. All right, so let's make some remarks about these Serre twisting sheaves. So first of all, we should observe that they are actually sheaves. All right, what are the restriction maps? Well, restriction maps are easy, right? Because if you restrict to a smaller open subset, you just take exactly the same element, and the only thing now is that there's less restrictions on F. So you can just take the same element there, and those are your restriction maps. What about the gluing maps? Well, you know, if you have two things and they restrict to match on a smaller open subset, then, well, this G over F, you know, in the fraction field has sort of a unique representation. If, you know, you cancel out all the common factors. So if they agree on a smaller open subset, then they must have sort of come from the same thing. So they sort of trivially glue. So, so this is not too hard to check. All right, let's talk about part B. If you take OPN of 0, this is actually isomorphic to the structure sheaf OPN. So remember we defined the structure sheaf on the projective space to be locally a quotient of homogeneous polynomials of the same degree. So in the case that D equals 0, then that's just saying F and G have the same degree. And you know, everything here is that we're on a unique factorization domain. So you know, locally a quotient of polynomials is the same as globally a quotient of polynomials. So this is all good. Okay, and let's notice there's some bilinear maps. So if I take OPN of D on U cross OPN of E on U, we can map that to OPN of D plus E on U just by taking, you know, F1 over G1, F2 over G2. It just maps to the product, right? Okay, and you can check the numbers work out. So in particular, okay, well, in particular, we see that OP, so let me say it this way. In particular, when D equals 0, OP n of E is an OPN module. Okay, so that's what I want. That's what I was getting at, is that these are actually sheaves of modules according to our definition, and the action is just given by as a special case of this action here. So you just you know, take your F over G or your G over F and multiply it by a fraction of degree 0, and you get something that still works. Okay. All right, now we got the basic facts about this. Let's get more facts about the Serre twisting sheaves. So for part A, let's think about the global sections. So if I have OPN of D and take the sections over the whole space Pn, what's that going to be? Well, in this case, we have to have that the denominator F is not equal to 0 on all of Pn. Okay, by the Nullstellensatz, so Nullstellensatz, this implies that F is a constant, right? If you have a non-constant polynomial, it's going to be 0 somewhere on the projective space. All right, so that, and then you can absorb it into the numerator. So it follows that the sections on the global sections are just the degree D homogeneous polynomials in this polynomial ring, right? So in particular, if If D is a negative, then there's no global sections. Zero. Of course, just because a sheaf has no global sections are zero doesn't mean the sheaf is zero. So, for example, if we take U0 in P1 to be defined as the standard open set, right? Points with homogeneous coordinates x0, x1, such that x0 is not 0. All right, so we'll take this open subset of P1, and let's look at the sections of O minus 1 on U0. Well, let me just tell you one of them, 1 over x0, right? So 1 over x0, the denominator doesn't vanish anywhere on U0, basically by the definition of U0, and this has a degree minus 1, matching up that, so that's good. So there's a section. Even though it has no global sections, it could still have some local sections. All right, let's now give an example of a morphism of OX modules. So let's pick f to be a homogeneous polynomial. And this will define for us a morphism of OX modules. OPN of D to OPN of D plus E. And let me describe the map just by writing phi maps to phi times F. All right, can you guess what this map is just from that description? Okay, well, of course, all it means is for any open subset U, you take your fraction here and then just multiply it by the new homogeneous polynomial of degree D, and you can think about the definition. That'll just increase the degree of the numerator by D, and so you land in, or increase it by E, and so you land in OD plus E, just like what you want. Okay, so that will give you a morphism of OX modules. Okay, interesting remark D. If we look at the structure sheaf and compare it to the twisting sheaf of D for D bigger than 0, we can see that these are not isomorphic. How? Well, by part A, we know their global sections are different, right? The global sections are the degree D homogeneous pieces of this polynomial ring. If they were isomorphic sheaves, they would have the same global sections, so they can't be the same. Okay, and in fact, they're not the same even for D less than 0, but that does not follow from part A. You need one more little thing. Maybe we'll talk about that later. Okay, but here's the interesting thing. So, but on UI, so remember UI is the standard open set on Pn where xi is not equal to 0. They are isomorphic. So if we take OP1, the structure sheaf, or not P1, sorry, this works for Pn. Let me change it to Pn. OPN of UI, not of UI, but rather restricting the sheaf to UI. This is going to be isomorphic to OD, restricted to UI. Okay, what's the map? So remember, so we talked about morphisms of OX modules, and of course an isomorphism of OX modules is just a morphism where all of the maps of sections are all isomorphisms, module isomorphisms, right? Okay, so how do we give the isomorphism here? Well, we can just take any section phi on any, so this is going to represent any section on any open subset of UI, right? Not just on UI, but any open subset of UI. And we can just multiply it by xi to the D power. Okay, that works anyway, even if you didn't restrict to UI. but it will have an inverse if it were restricted to UI. So the inverse will be given by taking phi and mapping it to phi divided by xi to the d. Okay, and this is perfectly okay because we're restricted to UI where xi is not equal to 0, and it's clear these are inverses. It works on sections over any open subset of UI. Okay, and of course the UI cover Pn, so we can say, we can see that OPN of D is locally isomorphic to OPN, but it's not isomorphic altogether. So such a thing is called a line bundle. So a line bundle is something that's locally isomorphic to the structure sheaf. And first thought, you might think, well, it's locally isomorphic, doesn't that glue to global isomorphism? The answer is no. It's possible to have a line bundle that's not equal to the structure sheaf, that's sort of somehow twisted in some way. So you get more interesting things. So this is a good example of that. So the textbook doesn't use this word, but this is very common in algebraic geometry to talk about line bundles. Okay, so here's a remark now that's sometimes useful. So if we have a map, an OX module morphism, so maybe we'll call it F. Now, so remember, OX module morphisms, so F and G are both sheaves of modules on the same space, right? Okay, so then for any P and X, we get an induced map FP from these stalks of the OX modules. All right, so and notice that FP is an OXP module. Okay, so let's break this down and make sure we remember. So OX of P is the stock of the structure sheaf FP. Remember, it is a local ring, and FP will be the stock of F at P. So remember, we just find stocks in general for sheaves, right? And it will naturally be an OXP module, where you can define the action just by taking any open subset and using the OX of U module action, and those will all be compatible no matter how small you pick them by the compatibility of restriction maps, right? And then the same thing for this FP. So FP is an OXP module homomorphism. All right, so that's a nice observation to make. And then I think there's an exercise in the notes that says that F is, so this is exercise, an isomorphism if and only if FP is an isomorphism for each P. All right, so you can think about that. All right, for the rest of this chapter, we're going to review some constructions, or not review, but learn some constructions that are useful for sheaves of modules. All right, so let's start with F, a morphism of schemes from X to Y, and let's have script F be a sheaf on X. All right, so from now on, whenever I say sheaf on some ring space, I'm going to assume that I mean a sheaf of OX modules. All right, so if you're working with ring spaces, the kind of sheaves you want are usually sheaves of OX modules. So sheaf will just mean sheaf of OX modules. All right, we are going to define a push-forward sheaf. So a little f push forward of big F is going to be a sheaf on Y. So we started with a sheaf on X, and we're going to use this morphism to push it forward to a sheaf on Y. So given any open subset of Y, so U will be an open subset of Y, the sections of the sheaf will be a F of F inverse of U. Right? So somehow you got to use F. In order to use F, you got to have an open subset of X. And if you have an open subset of Y, how do you get an open subset of F of X? Well, this little f is a continuous map, so we just take the inverse image and get an open set here. There we go. All right, and the nice thing about this is that this is actually a sheaf. It's not just a random sheaf, but it's a sheaf of OY modules. All right, so how does that work? Well, let's think about how we can define the action. So let's let lambda be something in OY of U, and it's trying to act on something in the push forward sheaf. Okay, and we'll just define that action to be, well, we can pull back lambda. So remember, a morphism of schemes comes with a pullback map that takes us an element of the structure sheaf of Y to an element of the structure sheaf of X on the inverse image, right? And then F push forward F of U by definition is just F of F inverse of U. So we'll just have the same phi here. Okay, and then this action here makes sense because this is just OX of F inverse U acting on the OX module F, right? So that's all good. Okay, and let's relate this. I mean, we can already see this is how this is sort of related to the morphisms of schemes, but let's make this make the connection even closer. So let's look at let's recall that to define a morphism of schemes, we needed a pullback map. Or rather, pullback maps. F pullback of U that takes functions on Y, right? So OY U and pulls them back to X like this. All right, and then they had to satisfy some compatibility conditions. This data, together with its compatibility conditions, can be viewed as a morphism of sheaves. F. We'll just name it F pullback. That goes from OY mapping to the push forward of OX. Right. So if I plug in U here, I'll get a map from OY U mapping to this. But by definition, this is the same thing as this. All right. So this morphisms of sheaves is the same as giving the data these pullback maps, and if you check the compatibility conditions that we required on these pullback maps, is exactly the same as the compatibility conditions for morphisms of sheaves of modules. All right, so we can think now of the pullback as being a map of sheaves of modules. Is maybe a nice way to look at it. Of course, we also had the condition on the local rings, which is not included in general here. Sorry, let me say that again. The condition on local rings, to be those required to be morphisms of schemes, is not included in the requirement of this being a map of the sheaves of modules. Okay. All right, let's do an example of a push forward, a more concrete example. So let's let P be a point in a variety. So P is just a single point and Y is a variety. Okay, and let's have I be the inclusion map from P to Y. All right, so considering P to be a subvariety of Y. Let's think about the structure sheaf on P. So P is a single point, so this is not going to be too complicated. There's only two open subsets. OP of P will just be the field, the ground field K, the sections of OP and P. P is just the ground field K. And the sections on the empty set will just be 0. Let's try and understand the push forward sheaf if we take I push forward of the structure sheaf of P. So this is now a sheaf on Y. What is it? What are the sections on an open subset U? Well, by definition of the push forward, this is just OP of I inverse of U. Now, what is I inverse of U? I mean, I is just the inclusion of a point into Y. So I inverse of U is either just P if P is in U and empty otherwise. So we get the sections are just field K if P is in U and 0 if P is not in U. Okay, and we can also look at the pullback map. Is considered as a map of modules like this. And this is really just evaluate a regular function at P. Right, so if you think about what the pullback map is, right, the pullback map is just function composition. So you take P, you include it into Y, and then you compose with the regular function. So that's just evaluating the regular function at P, and you get an answer in this field K right here, or maybe this K here. Those are the same K. All right. This example is sometimes called the skyscraper sheaf. At P, somehow you have this variety Y, but all the information of the sheaf is concentrated at one single point. So it's the skyscraper sheaf is something tall at one point. Sometimes it's called KP. Once again, this is kind of suggesting that it's equal to, you have the field K at the point P, and that's all the information there is. So this is K subscript P. All right, so these examples actually do come up sometimes, skyscraper sheaves. All right, so we're about halfway through the section about sheaves of modules, so I think we'll take a pause for today and try and finish it up on Friday.